Now, if you have a spring with a weight attached to the free end, if it's in its equilibrium position or its natural length, so as it would be in part A, then maybe you either push up or pull the spring down with the weight and release it. Then the elasticity of the spring would cause the weight and the spring itself to just bounce back and forth in an oscillatory motion. This is what we call a simple harmonic motion, and that kind of motion can be modeled using either a formula of the form S of t equals a cosine of omega t or S of t equals a sine of omega t. And which one you use, the sine or the cosine, depends on, do you start out at equilibrium? In other words, do you start out with position equals 0? Which of your trig functions, sine or cosine, starts out with an initial y value of 0? That would be the sine function. So if you start out with equilibrium, we'd be starting out with a position function that is a sine function. If you pull the weight down to release it or push it up to release it, something like that, then we'll talk about that being a cosine function. We've done these before a lot. Remember, A is just the magnitude or the amplitude of the function, and omega is our what we used to call B. So the amplitude here would be A, and the period would be 2 pi over omega. Now, when we talk about period, that's the amount of time it's going to take to get one full oscillation. The frequency, on the other hand, is how many oscillations do you get in 1 unit of time. Okay, so frequency is just the number of oscillations per unit of time. And it is always true that frequency is the reciprocal of the period. So for example, if you have a period of, say, 2 seconds, so it takes 2 seconds to get one full oscillation, that means that you would get 1/2 of an oscillation in 1 second. So that's when we take the reciprocal to find the frequency. Okay, so what if we have an object attached to a coiled spring that they've shown us here? It's going to be pulled down a distance of 5 inches from its equilibrium and then released. The time for one complete oscillation is 4 seconds. So what, in trig terminology, what do we mean when we say the time for one complete oscillation or one complete period of the function? That's going to be your period. Okay. How far we go down or up away from equilibrium, that's how far it's going to bounce away from equilibrium, and so that's going to be your amplitude. So for this particular problem, our amplitude will be 5, and our period, which is 2 pi over omega, is going to be 4 seconds. So we can use this to solve for that omega, or that would be 2 pi is equal to 4 omega, or that will be 2 pi over 4. Now, since we did not start at equilibrium, we pulled that weight down before releasing. Our position function will be given by a cosine function. So we'll have S of t equals a cosine omega t. We know that omega is pi over 2, so that's going to be cosine of pi over 2 t. And I'm going to write something that's wrong here just for a second, then I want you to tell me why it's wrong. If I put 5 here as my a value, why would that be incorrect? Actually, the multiplying part will be correct because it's a cosine of omega t. Remember, that's going to be the amplitude. But did we push this up 5 units or bring it down 5 units to start? We brought it down 5 units to start. So in this particular function, if we were graphing the position function, if we did 5 cosine omega t, it'd be going like this. We actually started down here, and then it's going to oscillate up and come back down. So rather than saying 5 cosine omega t, it will actually go down to -5. So while the amplitude is 5, since we went down first, A will actually be -5. Does that make sense? Okay, now if you want to find the position at t equals 1.5 seconds, it is as simple as plugging 1.5 into your position function for t. Just make sure when you do this, and I had a calculator earlier, okay. Make sure when you do this, you change your mode to radian mode first, because I don't see a degree on anything in this problem, so we know we're talking about radians. And so we're just going to have -5 times the cosine of, pi over 2 and then times 5. Okay. And you can, if you wish, go ahead and multiply the pi over 2 times 5 outside and then plug it in if you want to. Okay. Oh, except I changed that to 5 seconds. It was supposed to be a 1.5, wasn't it? Let's go 1.5. Let me change that to 1.5. So we're going to get about a 3.54 units. Now, I don't know if this is inches or centimeters or what, because they didn't tell me that, but would this be 3.54 units above equilibrium or below equilibrium? If you think about this function, equilibrium is going to be your midpoint. And so when you go to positive 3.54, that's going to be something that's above your midline. So that's going to be 3.54 units above equilibrium, just in case they ask you to specify. Now remember, equilibrium is just the when we've got it sitting at the natural length of the spring, so we don't have any stretch down and we don't have any compression up. All right, is everybody okay so far? Okay. All right, let's find the frequency. We know that the period in this case was pi over 2. So that means it takes pi over 2 seconds. No, did I just write that? No, our period was 4, wasn't it? That was our omega. Our period is 4, so that means it takes us 4 seconds to do one full oscillation. And the frequency is just how many oscillations do you get per unit of time, or in other words, per second in this case. So the frequency will just be the reciprocal of the period. So we get 1/4 of an oscillation per second. Any questions about this one before we do another one? Always. Yes, you bet. All right, so this is just one of our problems from our homework. It says that suppose a weight on a spring has initial position S of 0 and a period of P. So they tell me in this case my initial position is 4 inches and the period is 0.6 seconds. we want to find a function in the form a cosine omega t that represents the displacement and oscillation of this graph, or of this weight. Okay, our initial position is 4. Okay, so specifically we have taken our spring, if this was its equilibrium, and instead of pulling down, we went up. So we went up 4 units. So our amplitude will be 4, and in this case, since we went up first, our A value will also be 4. If we had pulled it down 4 units, we would have had an A that was negative 4. If our period is 0.6, we want to find B. Now remember, your period is always 2 pi over whatever this number is. So it's going to be 2 pi over omega, and we know that that is 0.6. So 2 pi will be 0.6 times omega, or omega will be 2 pi over 0.6. Now we don't want to, I don't believe, bottom fraction and multiply, and you're going to get 20 over 6, which is 10 over 3. That's where I got that 10/3 times pi. So our position function for this oscillatory behavior would be 4 cosine of omega t. So we're doing a lot of the same things that we've been doing. We're just doing it in a slightly different setting. Now we're talking about, you'll have 4 cosine of 10 pi over 3 times 1. Make sure you're in radian mode. You guys plug that in and tell me what you get, please. -2? That's what I got too, Cole. Excellent. So what that means is after 1 unit of time, so after 1 second, our weight is 2 units, or 2 inches in this case, below equilibrium. Now, is the weight moving up, down, or neither when t is -1? Well, if you think about this, what does this function look like? We've just got a cosine function that started at 4, so this way. So this is 4, this is -4, and the period was 0.6 seconds. I'm going to go out a little bit further. I need to get more than just 1 period. So I'm going to go continue. Okay, so this would be 0.6 seconds. This one that we ran out of room for, let me pull over another piece of paper just a little bit. This peak would be at t equals 1.2. So where would this value be? What's halfway between 0.6 and 1.2? 0.9. So the t value of 1 would be moving, it would be like right between here and here, say. So we've got this t value that corresponds to this position at that particular time. Your graph is moving back point. So this guy would be moving upward at that time. Okay. Questions so far? All right. All right. Y'all are just wondering when the other shoe is going to drop, aren't you? Hopefully it won't. These are pretty straightforward. Now, oscillatory motion and harmonic motion in general, oscillatory motion, we're basically ignoring anything that involves friction or anything like that. So, but oscillatory motion in general is very useful for those of you that are engineering majors or physics majors, things like that. You'll see it a lot. All right, so what if we look at this in a little bit different light? They tell us that we have a pendulum of length 1/18 of a foot, and we want to find the period and frequency of oscillation of this particular thing. So what they tell us is formula. They tell us that the pendulum is equal to 2 pi square roots of L over 32. That's the period, where L is the length of the pendulum in feet. And P is the period. Okay, so we want to find this pendulum of length 1/18 of a foot. So what am I going to do? I'm just going to replace L with 1/18. And simplify to find my period. So that would be 2 pi times the square root of 18 times 32 is what? 576. So that would be 1 over 576. So notice we didn't even have to figure out the formula for this one. They gave it to us. We just have to plug in for the appropriate values. So we have 2 pi times the square root of 1 over 576 is 1/24. Or that would be pi over 12 for the period. Okay. If we know that the period is pi over 12, what does that mean? That means it takes pi over 12 units of time, which in this case is seconds, to complete one full oscillation, to go from bottom to top and back to bottom or vice versa. So if we want to know the frequency, frequency is the easiest thing in the world to find if you know the period of that. So we would have 12 over pi oscillations per second. So that's about what? So it's about 3.82. So this particular pendulum would have approximately 3.82 oscillations. But they asked for exact, so I left it. You guys ready to try one? All right. So this is also one from your homework, and it says a weight attached to a spring is pulled down 4 inches below equilibrium. Okay. They tell us the frequency is 5 over pi. Determine a model that gives the position. Let's at least start together, and then I'll let you guys work on it for a second. First question. will I be looking at an A cosine omega t, A sine omega t, and why? Yes, we are taking it away from equilibrium. Start with a cosine function. Okay. They tell us that we pull it down 4 units. Of 0 is -4, and they tell us that the frequency is 5 over pi. If the frequency is 5 over pi, what is the period? It would be pi over 5. So is omega, and write down your position function. I'll give you a couple minutes. When you get an answer, just let me know and we'll compare. Anybody find an omega yet? Are y'all still out there? The period is equal to 2 pi over W. Remember, this is just like our B from when we were just doing regular graphing of sine and cosine. That was always we always called it a B. For harmonic motion, they always call it omega or W. But remember, to find the period, you take 2 pi over whatever that number is, and that's the period. So y'all are looking to solve that equation for W. Gotcha. Okay. So when we do that, we'll have pi times omega is equal to 10 pi. So we've got W is just equal to 10. Excellent job, Jose. All right, so what would be the form of my function? A cosine omega t. If we want to know the period, we already did that because I find it easier. If you know the period, you can easily find W, but the period would be pi over 5. And this would be your negative cosine 10t. Any questions about that one? All right, so if you